Hello, chemistry people. Just a quick video on electrolytic cells, which is in 9.2 of the SL curriculum. Today in class, I talked about galvanic cells, but I ran out of time to talk about electrolytic cells, so I'm making this video so I can talk about them in a bit more detail. I'm going to be focusing on the differences between electrolytic and galvanic cells. And the key thing for me to remember is that we're only talking about electrolysis of a molten salt, which makes our lives a lot easier than even the VCE from the last time I taught VCE. So, galvanic cells. Basically, we start with chemical energy. A galvanic cell converts chemical into electrical energy. Chemical energy. So this is a galvanic. Oh, it'd be good if I could spell galvanic cell. Converting electrical energy into chemical energy, that's where an electrolytic cell comes in. So this is an equilibrium. That's why when you look at the SEP table in the data book, those are all drawn with equilibria. All of those reactions can work in either direction. It's just for some of them, in order to get a reaction to go backwards, we would have to supply energy. This is how a rechargeable battery works. At the moment, my phone is not plugged in. So it's using the chemical energy of the battery and converting it into the electrical energy that's running my phone. If I plug in my phone, it's taking the electrical energy from my power supply and converting it back into chemical energy and recharging that battery. Rechargeable batteries are this equilibrium, literally in a case. Okay, so let's go into a bit more detail here. So, galvanic reactions are, galvanic cells are spontaneous. Electrolytic cells are non-spontaneous. And I mean that in the full sense of spontaneous and non-spontaneous from our Gibbs stuff, for those of you studying HL. So what we end up with is this reversible set of reactions. Now, one thing that we only look in HL at electrolysis of molten salts, so melted ionic compounds. Okay, so if I have a crucible with liquid potassium bromide in it, set up to a power supply. So this is the negative end of my battery and this is the positive end of my battery. If this is PbR2 liquid, start by listing down the ions that you have in this liquid. So in this liquid, I have Pb2 plus and Br minus. So, unlike before, where my negative and positive electrodes were defined by the reactions that took place and whether those reactions were spontaneously giving up or taking electrons, in an electrolytic cell, my positive and negative electrodes are defined by my power supply, by my battery. So I've shown you here that I've got my battery and I've got my negative electrode and my positive electrode. those, as you can see here, are defined by that battery. So I am basically pumping electrons onto this electrode and ripping electrons off this electrode. So if I am adding up electrons on this right-hand electrode, it is becoming more negative. It is going to attract the positive ion in my liquid. If I'm ripping electrons off the left-hand electrode, it's becoming more positive. It's going to yoink, yes, technical term, my negative ion. So at this right-hand electrode, I have Pb2 plus liquid, and I'm adding electrons to it, and I'm making lead. Now, this is where it becomes tricky. A couple of years back, there was an IB question asking about the full overall reaction for what happens at these electrodes with state symbols. Now, it told you that the melting point for this, I think this is something like 800 degrees C. Might be less. Give me a sec. Oh, wow, I was way out with that one. It wasn't 800, it's 373 degrees C. So, you were told in the stem of the question that lead bromide was melted at 373 degrees C or 380. And you had to give the full equation with the state symbols. Where a lot of students mixed up is that they said lead solid. Now, at the front of the data book, it's just after our standard periodic table, there is a periodic table that says melting and boiling points of the elements. Lead actually melts at a lower temperature than this. So one of the marking points was that lead was a liquid. So they may do that again, just being tricksy. So there's that. So I have pumped on my right-hand electrode, I am pumping electrons on to my lead ions and turning them back into liquid lead. And then on my left-hand electrode, I'm taking bromide ions and ripping electrons off them to form bromine molecule and 2 electrons. So that's a liquid. Bromine is a gas. Okay, let's talk about defining those electrodes as cathodes and anodes. So red cat, reduction takes place at the cathode. So now that we've worked out that we've got a reduction reaction, this is reduction, which means that this must be the cathode. Now remember, cathode is talking about the actual electrode, the thing that is carrying the electricity, not the reaction itself. The cathode is the place where reduction happens. The anode is the place where oxidation happens. Okay, let's work through another one of these. So the reason I'm drawing a crucible is one of the easiest ways to do this in a lab is to actually have a crucible of your stuff. So let's go with sodium chloride liquid. Let's set up exactly the same way as we did before with our positive and negative. What I'd like you to do, pause here and go through that process of labeling just like we did this guy here. Okay, I'm going to hope that you've done that. So remember, with the first thing I'd like you to do is always identify the ions that are present. That's always going to be your first step. Okay, so this is our negative electrode as defined by the battery, and this is our positive electrode as defined by the battery. So the negative electrode is going to attract the positive ion, and the positive electrode is going to attract the negative ion. So I am going to have sodium plus liquid plus an electron makes sodium. I'm going to guess that's a liquid. I remember from bonding, ionic substances tend to have higher melting points than the metals. And then on the other side, I'm going to have chloride ion forming half a chlorine molecule and an electron. And that's going to be liquid and that's going to be gas. Okay, let's go through and label cathodes and anodes. So we start by identifying what is our reduction reaction and what's our oxidation. So our reduction reaction is happening at that negative electrode, and by definition, the electrode that reduction happens at is our cathode. The electrode where oxidation takes place is by definition the anode. Okay, so in the IB, you only have to care about molten salts. So let's work through. Electrolytic cells convert electrical into chemical energy by bringing about non-spontaneous processes. We've talked about that. Oxidation occurs at the anode and reduction occurs at the cathode. And we've talked about them having the opposite charges. To me, it doesn't matter that they've got the opposite charges. By definition, oxidation occurs at the anode and reduction occurs at the cathode. What charge they've got, that's up to the business of whether it's an electrolytic or a galvanic. Reduction always takes place at the cathode. We have constructed and annotated them. We haven't talked about how current is conducted. Let's go and do that. Let's talk about electron and ion flow. We did that in the lab last year, and we've talked about deducing the products of electrolysis. Oh, and that's for galvanic, so it doesn't apply to what we're talking about. So let's talk about current, electron, and ion flow. So for an electrical circuit to function, it needs to be a circuit, a closed loop. My charges need to be able to get from one end of my battery, let me just get my highlighter, need to be able to travel from one end of my battery all the way through to the other. My charges need to be able to move. So up here in this external part of the circuit, I have electrons doing the moving, but I've still got this bit in the middle where it's not I don't have electrons to move. I don't have electrons just wandering about in solution. That's not how electrons work. In chemistry, it might be different in physics. So in here, I have lead ions and bromide ions, and it isn't just those two, there's stacks of them floating about. And they move, and they're the ones that connect my anode to my cathode. Remember when we were talking about properties of substances? And in order for something to conduct an electrical current, there had to be moving charged particles. In here, I've got my liquid lead bromide, which are moving because they're a liquid, and they're charged because they're ions. In a galvanic cell, it works slightly differently, and that's why we need a salt bridge. So, yes, and yes. Okay, fantastic. Thank you so much. I will get some question bank questions for my class about electrolytic and galvanic cells. Have a lovely rest of your day, and I shall see you next time. Bye.